What's up? Welcome back to my probability and SMP preparation channel. Daniel's here, and today I'm going to show you how to find a transformation of one or more random variables. First, I'm going to start off with the most basic case, a transformation of a random variable x. Then I'm going to continue to work on the more complicated case, a transformation of jointly distributed random variables x and y. Sum of some random variables, the maximum minimum of a collection of independent random variables. And the last thing of today is order statistics. So now let's look at the most basic case, a transformation of a random variable x. So a random variable x is either discrete or continuous. Suppose x is a continuous random variable with PDF f capital X of x and the CDF capital F capital X of x. And suppose that u of x is a one-to-one function. As a one-to-one function, u has an inverse function v, so that v of u of x is x. The random variable y is equal to u of x. Y is a transformation of x. And the PDF of y can be found in one of the following two methods. The first way, we simply apply the formula f capital Y of y is equal to f capital X of v of y times the absolute value of the first derivative of v of y. The second method, we apply the second method when u is a strictly increasing function. So in this case, in this method, we start with the CDF. The CDF of y, capital F capital Y of y, is equal to probability that the random variable y is less than or equal to little y. And since y is u of x, y is a transformation of x, so we replace y with u of x. So we got probability that u of x less than or equal to a single value y, little y. Now since u is a strictly increasing function, so u of x less than or equal to y, this is equivalent to x is less than or equal to u inverse of y. And u's inverse is basically v, because v is the inverse function of u. So this becomes probability that x less than or equal to v of y. And we got the CDF of x at the point v of y. Now we got the CDF of y. To find the density function, we simply take the first derivative respect to y. So the density function little f y of y is the first derivative of the capital F y of y. For discrete case, suppose x is a discrete random variable with probability function f of x. If u of x is a function of x and y is a variable defined as y is equal to u of x, then y is a discrete random variable with probability function g of y is summation of f of x, where y is equal to u of x. Now look at an example. The random variable x has an exponential distribution with a mean of 1, and the random variable y is defined to be y is 2 natural log of x. Find the PDF of y. So here y is 2 natural log of x. This is equivalent to x is e to the y over 2. And I'm going to notate this function as v of y. So little x is simply v of little y. And I'm going to take the first derivative of v of y. So v prime of y is 1/2 e to the y/2. The PDF of x, since the random variable x has an exponential distribution with a mean of 1, so f of x is simply e to the negative x, where x is positive. And the PD of y, we are going to find it using the transformation formula. So fy of y is first f of x at v of y, and v of y here is e to the y half, then times absolute value of v prime of y. F of e to the y half is 2 natural log of e to the y half, and v prime of y is 1/2 e to the y half in absolute value. Then simplify this, we have y half e to the y half is the PDF of y. So the PDF of y is y half e to the y half. Now we consider a two-dimensional case of a transformation. A transformation of strongly distributed random variables x and y. Suppose that x and y are strongly distributed with Chern density function f of xy, and suppose that u and v are two variables defined as u is u of x and y, and v is v of x and y. The Chern density function g of uv of u and v is defined as g of uv is f of k times with the Jacobian determinant. So here x, h, and k are the two inverse functions of u and v, and the last term is the Jacobian determinant. Let's look at an example. Suppose that x and y are independent exponential random variables is with mean 1, and suppose that u is y over x and v is x. Find the Chern density function of u and v. So here, look at the formulas. We need first the density function, the Chern density function of x and y. Then we need x and k and the Jacobian determinant. So to find f, the Chern PDF of x and y, remember x and y are independent, so the Chern PDF of x and y is the products of the two PDF of x and y. The PDF of x is e to the negative x, and the PDF of y is e to the negative y. So the Chern PDF of x and y is e to the negative x minus y, and x is positive and y is positive. So we have found f. Now we need to find x and k. So start with the second piece of information. U is y over x and v is x. We are going to solve for x and y in terms of u and v alone. So y here is xu and xav, but we don't expect to have x in the new function. So we are going to replace x by v. So y is uv and xav. The first uv here is notated as a function k of two variables u and v, and v here is the second function h of variables u and v. Then we find a partial derivative respect to u and v. So now we're going to apply the formulas because we have got everything we need to find the Chern PDF of u and v. First, f of xuv kuv is basically f of v uv, and the Jacobian determinant. F of v uv is e to the negative v minus uv. So we basically replace x by v and replace y by uv. And the Jacobian leads to v because v is positive. So the Chern density of u and v is v e to the negative v minus uv, where u is positive and v is positive. Now we consider some random variables. There are a couple properties that we need to memorize before we take the exam. The first property, if x1 and x2 are two random variables, and y is the sum of the two random variables, then the expected value of y is the sum of the expected value of the two random variables. And the variance of y is defined as variance of x1 plus variance of x2 plus two covariants of x1 and x2. Here, because the question didn't indicate that x1 and x2 are independent, so we have the term two covariants. If x1 and x2 are independent, covariance of x1 and x2 is 0, so the last term will disappear. Property 2, if x1 and x2 are two non-negative integer-valued discrete random variables. Here we focus on discrete random variables. With shown PDF f of x1, x2, then for an integer k non-negative, we have probability that x1 plus x2 is equal to k is a summation x1 goes from 0 to k, f1 of x1 times f2 of k minus x2. So remember, for discrete random variables, we always go with summation. Now we consider continuous. If x1 and x2 are two non-negative integer-valued continuous random variables with shown PDF f of x1, x2, then the density function of y is x1 plus x2. So fy of y is the integral from negative infinity to infinity of f of x1, y minus x1, d of x1. Property 4. If x1, x2, x3 to xn are random variables and y is a summation of xi, then the variance of y is summation of I go from 1 to n, variance of xi, plus 2 double summation I from 1 to n and j from I plus 1 to n, covariance of xi and xj. Property 5. If x1, x2 to xn are mutually independent random variables and y is a summation of xi, then variance of y is summation of variance of xi because they are independent. And the moment generating function of y, my of t, is the products, the Kessler products of the moment generating function mxi of t. Property 6. If x1, x2, xn and y1, y2 to ym are random variables and a1, a2 to an, b, c1, c2 to cm, and d are constants, then the covariance of this combination, summation of ai xi plus b and summation of cj yj plus d, is computed as double summation of ai cj covariance of xi yj, where I goes from 1 to n and j's go from 1 to m. Central limit theorem. Before I start the central limit theorem, I want you to notice here that central limit theorem is extremely important on the exam, and we always have questions relating to central limit theorem. So this is one of the things that you cannot neglect when you study and practice for SMP. Suppose x1, x2 to xn are independent random variables, which are identically distributed with mean mu and standard deviation sigma. Unless yn is a summation of these n random variables. Here I notated n because yn is basically depend on the number of random variables. If you have 10 variables, then this is y10. If you have 20 variables, then this is y20. But this is not the index. N here means the number of variables combined in this combination. So yn approaches normal distribution with mean n mu and variance n sigma squared when n increases. So for central limit theorem, it say that when the number of random variables increases, the distribution of the sum or the average will approach the normal distribution. And when an exam question asks for a probability involving a sum of a large number of independent random variables, it's usually asking for central limit theorem. So this is one thing that you should keep in mind when you practice for SMP. This is extremely important. Next, maximum or minimum of a collection of some random variables. Let's x1 and x2 are the two independent random variables with the CDF f1 of x is probability that the first variable is x1 less than or equal to x, and f2 of x, the CDF of the second variables, is probability that x2 less than or equal to x. We define two new random variables u and v as follows. U is the maximum of x and y, and v is the minimum of x and y, and x1 and x2. And we wish to find the distribution of u and v. So let's look at the maximum first. The distribution of the max u can be calculated using the CDF. So we start with the CDF of u. Capital F u of x is probability that u less than or equal to x. And u here is the maximum of x1 and x2, so we replace u by maximum. So probability that maximum x1, x2 less than or equal to x. And to ensure that the maximum of x1 and x2 will be less than or equal to a value little x, both x1 and x2 should be less than or equal to x. And because x1 and x2 are independent, so we can use product rule. So let's say probability that x1 less than or equal to x times probability that x2 less than or equal to x. And the first factor is basically the CDF of the first variable, and the second factor is the CDF of the second variables at the point x. So the CDF of the maximum is basically the products of the CDF at that point. For the minimum, we also start with the CDF. So remember the trick: for maximum and minimum, start with the CDF, not the PDF. Once you got the CDF, you can take the derivative to find the PDF. So here we start with the CDF of v. There is probability that v less than or equal to x, and v here is the minimum of x1 and x2. So the minimum of x1 and x2 less than or equal to x, so that means either x1 less than or equal to x, or x2 less than or equal to x, or both. But it's become quite complicated if we divide into cases to work on this problem. So I'm going to use complement rules to reverse the problems, to modify the problems. So by complement rule, probability that the minimum of x1, x2 less than or equal to x is 1 minus probability that the minimum is greater or equal to x. Here it should be minimum, but I dropped the minimum here. And to ensure that both the minimum of x1 and x2 to be greater than or equal to x, both x1 and x2 should be greater than x. And we can use products here because x1 and x2 are independent. So this becomes 1 minus probability that x1 is greater or equal to x times probability that x2 greater or equal to x. And this factor is 1 minus f1 of x. And this factor is 1 minus f2 of x. So this is how we find the distribution of the minimum and the maximum of a collection of some random variables. Order statistics. So what's order statistics? Suppose that you toss a fair coin 7 times and result in 4, 5, 1, 2, 6, 6, 3 as the numbers that come up on the face of the die at 7 times respectively. So the order statistics, basically we rearrange the sequence of result in increasing order. So if we sort those numbers in increasing order, we have 1, 2, 3, 4, 5, 6, 6. So here, by the third collection of number, we have x1 is 4, x2 is 5, x3 is 1, x4 is 2, x5 is 6, x6 is 6, and x7 is 3. After we rearranging the sequence of number in increasing order, we got y1 is 1, y2 is 2, y3 is 3, to y7 is 6, So here from x1 to x7, we rearrange and we got a new set of number y1 to y7. So y1 to y7 is called the order statistics of x1 to x7. So one thing we notice here, y1 is basically the minimum and y7 is the maximum of this sequence. We have learned how to find the minimum and the maximum. What about the number in the middle? So now what is the distribution of an order statistic yk? That means the number at the k position in the increasing order set of numbers. The minimum and the maximum easy. We have learned how to find it. So to describe the distribution of each of the order statistics y1, y2 to yn of the set of number x1 to xn, the density yk, the density of yk can be described in terms of the CDF f of x, the PDF f of x of a random variable xs. Gk of t is n factorial over k minus 1 factorial times n minus k factorial. Capital Ft to the k minus 1 times 1 minus capital Ft to the n minus k times f of t. So for minimum and maximum, the problem is easy. But for the number in the middle, we need to apply these formulas. But usually on the exam, we don't really see this question often. So make sure you know how to find the minimum and the maximum. Those are more important. So that is everything for lesson 8. Now we practice on some problems. Problem number 1, the profit of a new product is given as z is 3x minus y minus 5. X and y are independent random variables with variance of x is 1 and variance of y is 2. What is the variance of z? This question is quite simple. We need to apply one of the properties that we learned in the some variables. So variance of z is variance of 3x minus y minus 5. This is equal to 3 squared variance of x. 3 squared is 9 plus variance of y. And this is equal to 9 times 1 plus 2. The answer is 11. Problem number 2. Let time t that manufacturing systems is out of operation has cumulative distribution function capital F of t is either 1 minus 2 over t whole square when t is greater than 2 or 0 otherwise. The resultant cost to the company is y is equal to t squared. Determine the density function of y for y is greater than y is greater than 4. So this is a question of transformation of one single variable. So to apply the formula in this question, we're going to apply the first formulas, the formulas for transformation. So we need to find the transformation function. We start with y equal to t squared, so t here is square root of y, and I'm going to notate this one as a function u of y, where y is greater than 4 because t is greater than 2, so y should be greater than 4. And the u prime of y is 1 over 2 squared y. Now we find the CDF of t because we are given this CDF, we're not given the PDF, so we need to find the PDF. For t is greater than 2, the density function of t is the first derivative of the CDF. And that's equal to 2 times 2 over t times negative 2 over t squared. That's equal to 8 over t cubed. And here is applied for t is greater than 2. So now we have found the PDF of t, the transformation and the derivative. So we're going to apply the transformation formula to find the density function of y. The density function of y is defined as g of y is f of square root y times u prime y in absolute value. And that's the 8 over y square root y times 1 over 2 squared y. And the answer is 4 over y squared, where y is greater than 4. So the density function of y is g of y is equal to 4 over y squared, where y is greater than 4. Problem number 3. Let x and y be two independent random variables with moment generating function f x of t is e to the t squared plus 2t, and my is e to the 3t squared plus t. Determine the moment generating function of x plus 2y. So here I'm going to call z as the variables. Z is x plus 2y. Then the moment generating function of z is mz of t. This is equal to expected value of e to the tz by definition. And now we replace z, we substitute z by x plus 2y. So this becomes expected value of e to the xt plus 2yt. And use the property of exponential of exponents. We got this is expected value of e to the xt times expected value of e to the 2ty. For the third term, the third factor is basically the moment generating function of variable x. So this is equal to mxt, and is e to the t squared plus 2t. Now the second terms, the second factor is a bit tricky here. You can realize that this is basically the moment generating function at the point 2t, not t. So if you can recognize the trick here, the problem becomes very easy. So the expected value of e to the 2ty is the moment generating function of y at the point 2t. And this is equal to e to the 3 times 2t squared plus 2t. We basically replace t in the second moment generating function by 2t. And we got e to the 12t squared plus 2t for expected value of e to the 2ty. Now we multiply them together to get the moment generating function of z. So the moment generating function of z is e to the t squared plus 2t times e to the 12t squared plus 2t. And this is e to the 13t squared plus 4t. By the way, on the exam, it's quite often that you have to encounter the question related to moment generating function. So moment generating function is the part of knowledge that you cannot skip. Problem number 4. Let x1 and x2 be random variables with joint moment generating function f of m of t1, t2 is 0.3 plus 0.1 e to the t1 plus 2 plus 0.2 e to the t2 plus 0.4 e to the t1 plus t2. What is the expected value of 2x1 minus x2? So for these problems, first we look at this expected value. E of 2x1 minus x2 is 2e of x1 minus e of x2. Now to find e of x1 and e of x2, we basically partially differentiate the moment generating function respect to t1 and then respect to t2. Expected value of x1 is the partial derivative of the moment generating function respect to t1 at the point 0, 0. So we differentiate this function respect to t1, and then we substitute 0 at both t1 and t2. So 0.5 is the expected value of x1. To find expected value of x2, we partially differentiate the moment generating function respect to t2 and then substitute both t1 and t2 as 0. And 0.6 is the expected value of x2. So now we use these two pieces of results to find the expected value of 2x1 minus x2. So expected value of 2x1 minus x2 is 2 times 0.5 minus 0.6, and we got 0.4 is the answer. Problem number 6. A charity receives 2025 contribution. Contributions are assumed to be independent and identically distributed with mean 3,125 and standard deviation 250. Calculate the 98% percentile for the distribution of the total contribution received. So this question asks for the total contribution received. That means the summation of the 125 random variables. So the total contribution received y, which is the summation of x. Then y here would follow normal distribution because is by a central limit theorem. Remember, whenever you see a large number of random variables, that means you have to think about central limit theorem. So by central limit theorem, y should follow normal distribution with mu of y as 125 e of x, which is 125 times 3125, and the answer for the mean is 632 is 6,328,125, and the variance is 225 times 250 squared, and then we take the square root to find the standard deviation. So the standard deviation of y is 1150. Since y here follow normal distribution, so to find the 90 percentile, let's call y 90 is the 90th percentile for the distribution of total distribution claims received. We have probability that y less than or equal to the 90th percentile should be 0.9. And use standardization, we have this equivalent to probability that z less than or equal to y90 minus mu y over sigma y, which is 0.9. So y90 minus mu y over sigma y is basically z upon 1. So we can find y of 90 is 1.28 times sigma y plus mu y, and this equals to 6,342,542. You can write to 6,343,000 for convenience. So thank you so much for watching my video. That's everything for today. I have only one more lesson to finish the series of SMP and probability. So hope you guys follow me next video. Bye.